In today's video lesson, we're going to cover the common ion effect. And now I think this is a good topic to review because it is frequently on the AP Chemistry exam as a key topic, but it also applies to a lot of different concepts like solubility equilibrium and Le Chatelier's principle. So let's look at the definition first. What is the common ion effect? So this phrase obviously is really important. We have to look for a common ion in a solution. So when we see a common ion in a solution, that will lower the solubility of a salt compound. And in terms of Le Chatelier's principle, what happens is common ions, when you have so many of them, they're going to cause my equilibrium to shift to the left towards the reactant or towards the salt. So let's make a note of that Le Chatelier's principle is involved because common ions will cause an equilibrium shift towards the reactant, which is the left of my chemical equation, and that also contributes to lowering that solubility. Okay, so for example, let's look at this first question. The molar solubility, I should say, of MgF2 in pure water is 2.6 times 10 to the negative 4 moles per liter. What happens to the solubility of MgF2 if we dissolve it in a solution of NaF instead of pure water? So now I always like to approach these questions by first writing down the dissociation equation. So MgF2, let's write that down, is a salt compound. We're going to write it with equilibrium arrows, okay? It is solubility equilibrium. So we're going to put those equilibrium arrows, and the ions that we dissolve are Mg2+, aqueous, and fluoride. Now, just be careful, we do have to balance the equation. So you have to put a coefficient 2 here, 2F minus 1 or 1 minus, aqueous. Okay, that's how MgF2 will dissociate. So again, in pure water, here's the molar solubility. That's fine. This is not a calculation problem. It's more of an explanation. So if I dissolve this, or if I try to dissolve this in sodium fluoride, you have to automatically ask yourself, what is the common ion? Okay, again, that's important. That's part of my definition. So NaF, this one will dissolve into sodium ions. We're not going to write the entire thing for this one. Sodium is 1+, fluoride is 1-. So we should be able to tell that fluoride is the common ion. You're going to have fluoride from NaF, and then you also have fluoride from MgF2. So what that means is that the concentration of fluoride is going to be increasing when we try to dissolve this in my sodium fluoride solution. Now let's think back to Le Chatelier's principle. So I've got an increasing concentration of fluoride that's on the product side. So what that will do is it's going to cause more collisions between these ions, which will then make my equilibrium shift to the left, which will basically decrease the amount of ions I have in solution and increase the amount of salt I have, thus lowering its solubility. Hopefully that makes sense. So let's write a little statement here. So we're going to say here that therefore the solubility of MgF2 will decrease when you try to dissolve it in sodium fluoride, okay? So I'll make this a little short form, so in sodium fluoride solution. So this will decrease. The reason is because of the common ion fluoride, right? Due to the common ion fluoride 1-. So the fluoride 1- ion will cause the equilibrium to move backwards, which again decreases that solubility. So due to the common ion fluoride, which causes, you can word this better, I'm just kind of thinking out loud here, which causes the equilibrium to shift left towards the salt. Okay, that's how we tackle a problem like that. I think a really good tip is to always write down the dissociation equation to help you identify the ions and then just to kind of visualize it. Okay, so let's try a more difficult problem. Here's one more example. In which beaker will AgCl be more soluble? So I have two beakers here, A, which is labeled as 50.0 milliliters of water, and B, which is labeled as 100.0 milliliters of 1.0 moles per liter sodium chloride. Before we, again, jump into the solution or the answer, AgCl, let's write down the dissociation equation. So again, we're going to use equilibrium arrows here. This will break down into silver ions. So silver 1 plus or plus 1, same thing, plus chloride. Chloride is 1 minus. Okay, so that's how silver chloride will dissociate. So then we need to ask ourselves, again, in which situation or which beaker will it be more soluble? Well, notice that in beaker A, even though you have less water, you don't have any other ion. There's no common ions here, okay? So no common ions in beaker A. However, in beaker B, we will see a common ion because the NaCl will dissociate into sodium ions and chloride ions. So we're going to have a common ion in beaker B of chloride. So in beaker B, we have a common ion of Cl1 minus, right? So once again, what will that do? That's going to increase the concentration of chloride minuses you have in beaker B. That will cause Ag ions and chloride ions to collide. You have more of that, greater concentration of those ions of chloride, causing my equilibrium to shift backwards, creating more AgCl solids in beaker B. So in which beaker will the AgCl be more soluble? It's going to be more soluble in the A because you don't have any common ions that are going to change the position of your equilibrium. Okay, so in this one, I'll just answer the question as stated. We're going to say that AgCl is more soluble in beaker A. And then we can say here, due to a lack of common ions and ... You can kind of fill in the blank there for more detail. Hopefully this video lesson helped you clarify this concept. If you want to see another example or more difficult examples, let me know in the comments, and thank you for tuning in. And if this helped you at all, it would be great if you could give a like and a subscribe, and thanks again for watching. Take care.